Hello friends, welcome to another tutorial in electromagnetics and antennas series. In this tutorial we'll talk about the classification of media in which a wave propagates based upon its properties. Now the reason I've selected this topic is that there is a lot of confusion regarding the lossless and lossy media, and in case that confusion persists, will not be able to understand the Maxwell's equations, the wave equations and their applications properly. So let's get straight into it. Before we discuss the single continuous media types, I'd like to highlight a few key points here. We'll discuss the properties of the lossless and lossy media based upon these parameters. So you must be very, for example, sigma is conductivity, epsilon is permittivity of the media, and this is the absolute permittivity of the media, which is given by epsilon naught into epsilon r, where epsilon r is relative permittivity and epsilon naught is the permittivity of the free space, whose value is fixed, which is 8.85 into 10 raised to the power minus 12 farad per meter. Or in some calculations you can use 10 raised to the power minus 9 upon 36 pi farad per meter. And the second set of parameters are mu, which is permeability of the medium, and it is given by mu naught, mu r. Mu r is relative permeability and mu naught is the permeability of the free space, which is given by 4 pi into 10 raised to the power minus 7 Henry per meter. The key points here are these units, so you must be aware of these units, and these values are extensively used in the numerical calculations. Now let's divide the single continuous media into two types. The first type of media would be lossless media and the second type of media will be lossy media. The idea of this video is to make you aware that a lossless media is that media in which the conductivity will be zero. So if there is no conductivity, there is no conductivity in the medium, that goes to show that nothing will be lost as energy loss or propagation loss or heat loss or any of that sort. So you must relate lossless term to something which has zero conductivity, where sigma is 0. So that's how you need to remember this. And for lossy media, the conductivity will be non-zero, and at some point it will be infinity. For example, if you see for perfect conductors, the conductivity is infinity. So if infinite conductivity is there, the wave will have complete freedom to move along on that media, but that complete freedom will also result in a lot of losses. So that is why it is known as lossy media. So the first key point is the division of the lossless and lossy media based upon the conductivity. So you must remember that lossless media is the one where the sigma is 0 and lossy media is the one where sigma is non-zero. For good dielectric, which is close to perfect dielectric or free space, sigma will be non-zero, but it will have a small little finite value that will cause some loss. Alright, now the second key point here is under lossless media you'll find two different media, perfect dielectric and free space. And what's the difference between these two? For free space, the epsilon will be of course epsilon naught and mu will be mu naught, which are the standard values for permittivity and permeability respectively. But for perfect dielectric, you can assume mu to be equivalent to mu naught, but epsilon is given by epsilon naught into epsilon r. So it will have a different permittivity from that of the free space. It will have some factor epsilon r, although that factor would not be significantly large, but it will have different permittivity than that of the air. But these two conditions, sigma is 0 and mu is equal to mu naught, they'll remain the same in lossless media. Alright, and when we consider lossy media, we encounter three different things now. We'll see good dielectric, good conductor, and perfect conductor. Please understand, out of these three, the only common thing is mu. So in all the three cases, mu will be mu naught into mu r. So that's one key point that you need to commit to your memory, that for a lossy media, the permeability will not be that of the free space. It will be different from that of the free space. And you know that for good dielectric, sigma will be approximately 0, but non-zero quantity that will result in some loss. For good conductor, it will be not infinite, very very high value, but for perfect conductor it will be infinite. So these 2 points are pretty easy to understand, that close to infinity and infinity will result in good conductor and perfect conductor respectively. And you see that for good conductor, the epsilon is going to be equivalent to epsilon naught, and for perfect conductor also epsilon is going to be equivalent to epsilon naught. Permittivity will be very very good for the E vector, and for good dielectric, the epsilon will be equivalent to epsilon naught into epsilon r. So this good dielectric can be related to somewhat the perfect dielectric case, where epsilon is equivalent to epsilon naught into epsilon r. So these are the conditions that you must remember for the classification of media based upon their properties. And one last thing that I want to touch upon is this value. This is known as the loss tangent, and the value of sigma upon omega epsilon is very very less than 1 for case of good dielectric, although we have the value of this to be equivalent to very very greater than 1 for some other case that is discussed in a separate video by the name of loss tangent. You can watch that video as well. But on a broader perspective, you must know the basic difference between a lossless media and a lossy media, and what are the conditions that prevail in both these media. So that's about it that I wanted to discuss in this tutorial. I hope you liked the content. If you did, give it a thumbs up, consider subscribing to the channel, and share this video as much as you can, and keep visiting the channel. Take good care of your health, stay inside, and I'll see you around. Take care. Bye bye.